Hi everyone. We will start in just a minute as we wait for everyone to join. In the meantime, feel free to use the chat and let us know where you're joining from. Okay, great. Hi once again. And again, thank you for joining. I'm Katie Ivanovska, Marketing Program Manager at Kumo, and I will be your host today. We are thrilled to have Mahdi Sajadi, Principal Data Scientist at Yieldmo, along with Joseph Oliveira, Data Scientist at Kumo, here with us for this exciting workshop on turning relational data into embeddings. It's important to mention that during this session, you will learn how and why generate embeddings for entities like transaction, customer, and inventory directly from your data warehouse, eliminating the need for time-consuming feature engineering. Also, application of relational or graph embeddings for predictive AI and generative AI, such as recommendation system and retrieval augmented generation, and also real-world example and lesson learned from applying relational graph embeddings to a large-scale recommendation system. Before we begin, please remember to use the Q&A section to ask any question throughout the session. At the end, we will dedicate time to answer the most relevant question in the order they are received. I hope that now we are ready to start, and let's dive in. I'd like to invite Joseph from Kumo to begin this workshop. Joseph, I believe you are more than ready. Over to you.
Yes, welcome everybody to our workshop, Jenny plus Jeans equals customers, where we'll be talking about embedding relational data for fun and for profit. And thank you, Madi, for joining me. So I'm Joseph Oliveira. I'm a data scientist at Kumo. I have my master's in statistics and background in data science. I've been in the industry for about 5 years. And I'm really excited to talk to all of you about embeddings and how you can generate them, how you can use them. And I've invited Madi to talk a little bit about how he uses them as well. So let's get started. I think where it makes the most sense to start is to first make sure we're all on the same page about embeddings. So what are embeddings? Embeddings are powerful representations of your data that capture concepts not explicitly encoded in the individual fields of the source data, which makes sense, but a lot of words, what does it actually mean? Now, for those of you that are familiar with embeddings, you use them already, don't worry, we're going to get into the weeds, but really want to make sure everyone is on the same page. And I think what makes the most sense here is to start first with a couple of examples. So a really common example, and one that's been around for a while since the introduction of Word2Vec, has been this kind of word algebra. Here, what's happening is we've embedded these particular words using the Word2Vec algorithm so that they have a numeric representation. And what this numeric representation lets us do is a little bit of word algebra, where we can take king, subtract man, add woman, and it approximates queen. So what's actually happening here is that because we've embedded these words, that embedding, that numeric representation is capturing some of these higher level concepts of what is a king, what is royalty, what is gender. And that information, though not explicitly encoded, was captured by the embedding. A great example on the internet of this word algebra available on GitHub by Anthony Liu here is an interactive example where you can plug in words. Here I've plugged in Germany plus Paris minus France. And when I do this kind of algebra with the words, you'll see a list produced of other countries and places and so on. With at the top of the list being Berlin, the capital of Germany. Again, these embeddings of words are capturing some of these higher level concepts about what it means to be a city, a capital city, a country. And by doing this kind of algebra, lets us approximate other embeddings that are close to the resulting algebraic kind of equation here. Now, embeddings extend to more than just text. You might have seen embeddings related to images, and where they are typically applied is in image recognition. Here's the MNIST data set with some of the embeddings projected so that you can see how these vectors, these particular numeric values, when you plot them, kind of show some of the relationships among images. And in this case, the colors represent the actual numeric value. And what this illustrates here is just, again, how embeddings capture some of these higher level concepts, not explicitly encoded. When you write a letter, you're not telling a machine exactly what to look for. Embeddings capture those higher level concepts. And so, again, just to kind of summarize, what are embeddings and some of the examples. We've seen the image embeddings, we've seen text embeddings, audio and video embeddings, and so on. So what's to stop us from looking at embeddings and capturing information from your relational database? And so how might you generate those embeddings from your relational database today? Now, here I have an example where I have this data schema, and consider an e-commerce platform where users are transacting and buying products. Maybe they're visiting the website a couple of times, and so there are sessions to their visits, and they're exploring different products, expressing intent to buy, but not purchasing yet. And then finally, they transact. This whole process, complex as it may be, you capture that in your relational database. And as data scientists, what we focus on is taking this relational database structure and trying to figure out how can we engineer certain features that capture this complexity, that let us tell a machine learning algorithm, these are the signals to pay attention to and learn from, which expresses intent to purchase. Maybe they've purchased recently, or they're particularly active in the last week or so. This type of feature engineering has served us well. However, you're still missing out on that complexity. Because see, the complexity really lives in the primary foreign key relationships that identify how your data schema is connected. And actually, in those relationships, when you flatten them out, you're losing that complexity. You're actively obscuring, that signal that relates how these customers are shopping, or whatever, in your case, your data expresses. So what can we do with this? Well, if we treat each table as a node and we connect the nodes together with the primary and foreign key relationships, what we end up with is a network graph. So as a result, to generate embeddings, we can simply use graph neural networks, and as input, we can treat our relational database as a graph. And this particular insight is one that one of our founders had, Yuri Leskovic, who, a professor at Stanford, pioneered the research and application of graph neural networks, and as well as developed the framework to perform this type of graph neural network application at scale for enterprise. So what does it take to build a graph neural network in enterprise? Well, it's actually very, very easy. First, you want to start off with just registering your data schema. And we'll see how that works in a moment. But once you register your data schema, you simply have to write a query as you would today. But in this case, you can use what we've developed as a predictive query language, a particular language that lets you define and formulate predictive tasks as simple as SQL. And lastly, let the GNN learn the features. This is a fully inductive process. Inductive meaning the GNN will learn from the data itself. You don't have to engineer features in particular. So to see what I mean, I have a great example here. This is the Kumo platform, and this is at the stage where we have registered our data. And we can see here, this is an e-commerce example. We have a customers table, we have a transactions table, we have a product table. And we can see how they're linked together. Customers that transact, there's a recorded foreign key customer ID that links together the customers to the transaction table. As when they transact, there's a product table and there's a product that they're purchasing. So this information resembles the schema of a common e-commerce database. We can click in and see more information about this particular table and see how the health is of our graph, how many elements in one table are present in the other. But this particular schema allows us to then treat our database as a graph. And what that lets us do is formulate a predictive query. Here, the query is, can I predict what customers might be interested in purchasing in the next 30 days? And we formulated this as a predict list distinct task, which means that we are predicting links that could exist in the graph between a product and a customer. And we're predicting the top 25 candidates for what those links could be for each customer. Now, to create embeddings now from this predictive task is quite simple. Taking a step back, we can just simply run a batch prediction job. And here I can specify if I want predictions and if I want embeddings. And by making the specification and maybe selecting, in this case, we're going to go all the way back to the great year of 2020. Selecting an anchor date for which I want to make my predictions for. I can come here and go ahead and submit this job and it will start running. The output of which will be recorded here. And in this case, it only takes a little over 15 minutes for this job to run. And it's recorded in my S3. And just like that, I've gone from having my database, registering it, running a predictive query, and generating embeddings. Now, this is a toy example meant to simply illustrate how simple that process can be. In reality, your database might look a lot more like the following. Much more complex with relationships that span several tables and certain fact tables that express how things are coded and charted. This here is an example of a database, perhaps within a healthcare setting, where we're particularly interested in understanding patients. And within the healthcare setting, patients are very complex entities. When they're admitted, they receive different medications. They might be admitted for different reasons, and they are diagnosed with different conditions. Their treatments vary based on several factors, and so on. And so instead of trying to flatten this out into a table, what if we can respect that complex nature and embed and create embeddings for patients that similarly capture that complexity? And so for that, that's exactly what we've done. And when we take a look in this example here, and understanding how patients might be admitted to a hospital, we can look at a use case such as readmission, understanding the risk of a patient who is currently admitted, but we're looking at discharging them. What is the risk of that patient being readmitted to the hospital within the next 30 days, indicating that they received insufficient care? So if we want to assess this readmission risk, and we want to use embeddings to help us do so, we can, the output of which looks a little like this. So remember, for embeddings, we record the embeddings to an S3 output, where I can then read that in. And here you might have your own particular production framework for leveraging and capturing the output of models, but we'll use this notebook in lieu of that. I'm reading my embeddings. I'm also, and here with my embeddings, I have each patient represented as an entity. The embedding itself, which I can see the list of different floating point numbers. This vector here is a particular embedding for a patient. And then I also have associated predictions, their risk of readmission, if you will. And here is what that output looks like. We have for each patient a binary true or false, will they be readmitted or not in the next 30 days, as well as a probability. Now, with working with embeddings, if you want to plot them or explore them and visualize them, you will need to use clever techniques, that project these particular embeddings, which are very long sequences of numbers, down to something more manageable, something like 3 or 2 dimensions. And for that, you might want to use algorithms like UMAP or TISNE or PCA, which projects high dimensional vectors down to lower dimensions for us to explore and visualize. And here I've done just that. I've prepped my embedded data, and I want to go ahead and project it down to just 2 dimensions here. And when I do that, now what I have is that each point represents a patient, and their coordinate on this plot represents that high dimensional embedding projected down. And then the shape of the point, whether it's a circle or a triangle, indicates their prediction as to whether they will be readmitted or not. And what's plain to see is that a lot of points in the upper left corner are patients that we are predicting not to be readmitted. Whereas the patients in this bottom left corner, if I zoom in, most of these are triangles. And these triangles indicate these are patients that are likely to be readmitted. And not only that, but the embeddings capture that about the patient. The fact that these points are all clustered together is significant because that comes from that embedding vector. And they're all very closely situated here. Now, the color also comes from clustering my data, and I'm using a k-means clustering algorithm just to identify clusters here. The techniques that you might use to embed and visualize embeddings are numerous, but these are just a couple of examples here of how you could do it. So kind of jumping back, why use embeddings? Why do all this? Well, embeddings will improve your existing model performance, downstream operations, and unlock opportunities for your data science team. And the way to really think about this might be to orient yourself around use cases that have been explored. So for example, in our customer segmentation use case, we saw earlier, we can create this e-commerce graph and look and capture that complex behavior exhibited by a customer of them shopping, looking around for different products, ultimately transacting. That graph-based approach accounts for customer interactions in a way that flat single tables will not. Embeddings incorporate various customer attributes, purchase history, and interactions, and they also capture how those customer segments evolve over time. But the thing is, embeddings are much more, or graph neural networks are much more general than that. And they generalize to entities beyond just customers. So here we can really look at it as graph-based embeddings accounts for any type of entity interaction. And they can incorporate various entity attributes as well as their history of interactions. And lastly, those embeddings can capture how those segments evolve over time, allowing for more dynamic and adaptive segmentation strategies. Filling in the blanks, we can look at it from our readmission example. Patients, we can segment patients out based on their different treatment regimens, and we can incorporate various patient attributes, their demographic background, their age, the medications that they're taking, their particular diagnosis, and recent outcomes. And lastly, we can see how patient populations evolve over time, allowing for more dynamic and adaptive segmentation strategies. But use cases extend much more beyond than just predicting how customers or patients or any other task, any other binary outcome. Since we're working with a graph neural network and our data structure is a graph, we can predict links that may exist in that graph. Say, patients that should be linked with a certain treatment, or financial instruments that may be linked to a certain action, customers with certain stores, or customers with certain products or brands. And maybe lastly, customers with ads. What ads should you show customers? So these are different use cases you can tackle with embeddings. And with that, I do want to introduce my co-presenter here, Matti, who is a user of Kumo and embeddings. And I'll hand it over to him to introduce himself.
Thank you. Thanks for the kind introduction. Hi, everyone. I'm very happy to be here. Thanks to Kumo for giving us this opportunity to present the work we do at Yieldmo. I'm going to go ahead and share my screen. My name's Maddie, I've been a data scientist for the past 6 years. My background is in physics, but then I made the jump and became a data scientist. And today I would like to present basically a use case of embeddings, and hopefully it's a process that it shows you how the business needs can be turned into a data science problem and how embeddings are leveraged to address that business need. Yieldmo is an ad tech company, so the use case will be related to ads. As you know, being exposed to ads is a very multi-dimensional experience. You have multimedia, like either it's image or a video. It could be, the user itself has some interests, and the website or the apps that are showing the ad also have some context. And all of these things come together to offer the user some hopefully useful information, and on the other hand, the advertisers to advertise their products or services. And the Yieldmo aspires to really optimize all these aspects at once, and that's basically what we do. What I would like to today to talk about is I would like to briefly show you what happens when you go on a website and see an ad. Hopefully that gives you a context of where data science and problems can be solved with like embeddings. So although when we go on websites, it's almost instantaneous to see an ad, behind the scene, a lot of operations are happening. When you go to a URL, whether you click on a link or you type a URL in your browser, the publisher, or in this case, the website, for example, sends a request to supply-side platforms, which Yieldmo is one of them. And we basically grab those information, we process it, we consider it, is it a good request, is it a bad request, and we could discuss what good and bad means in this context. And then we pass it on to demand-side platforms, which you could imagine they are representative of advertisers. And if everything works out, multiple DSPs bid on the same request, the one with the highest bid wins. And finally, a digital handshake happens and the ad is shown. And this entire process happens in, imagine, like 50 milliseconds. That's why it looks like very instantaneous, but in effect, all these operations are happening behind the scenes. And every decision that is being made in this process, there are models, logic is making that decision, basically. And so all of those questions can be solved with data science. In addition to that complexity of having a lot of decisions to be made in real time, we end up with an enormous data set. Yieldmo alone processes about 1 trillion requests per day. And all those requests are not just a signal of saying there's a user here. It comes with a significant number of features and information that can be used to make better decisions. So the data set is very long, it's an enormous data set, and it's also really wide. It has lots of different features. Some of those features that are more maybe obvious are things like the day part, like the time of the day that the ad is being shown, maybe the location of the user, the type of connections they have, the device they use, and also other environment features like if you have a phone and you're scrolling past an ad and you like it, so you go back, you could track those kind of swipes, things like that. We could track whether the click happened or the video was watched completely or not. All that can be tracked. And all these features naturally could go into a model and make a decision whether we want to show an ad or whether this is a good impression, the right audience, all that questions. And as I think Joseph set me up really well here, coming up with features is a very intense process. Not only it takes a significant amount of effort and time, there's always a chance that you miss a good feature, because it's not just using a column or table, because sometimes the right features are a combination, a functional combination of these features. And one of the reasons embeddings are very useful is basically a model learns what features are useful, and it creates these embeddings that are basically used for downstream models. In addition to these technical challenges, we had some business challenges. And data privacy is a very important trend, both inside Yieldmo and also, as an industry. And data privacy, the concern of data privacy is basically the effect of it is the number of users who are tracked via identifiers like cookies is going down, and the rising cost of reaching them, actually. So you pay more to reach less number of people. And more importantly is showing ads to people. If it's not relevant, it's the waste of money and time for everybody, including the user, SSPs, DSPs, and advertisers. Showing the relevant ads to the right person is the valuable effort that we should be aspired to, basically. And to take this business needs and technical needs, we started testing many different more traditional ones, and all the way to using embeddings via Kumo. And we eventually decided to use Kumo for our backend engineering and backend feature generation, basically. I would like to basically show you one of the use cases, how the graph emerges from our data and how the embedding helps us to achieve like at least one use case in our case. So in our data, you can think of what we have is a browsing data information. So we have a set of users who visit some web pages or some apps. They see the ads and they interact with them. And we can capture all of this in a graph that is like a bipartite graph of URLs and users. And maybe the frequency that the user goes to a website or the type of interactions they do, maybe they click on an ad and sometimes they don't. We could basically package all of this information, as Joseph showed, as basically tables in a database, represented as a graph, and then you take those entities and embed them in the same space. In that space, basically, the effect is the items that are similar to each other, they end up closer to each other. And the items that are not similar, they are far apart. So this distance between the items becomes the critical information that we need. And the entire information that we have in many, many tables that we have, the graph is very complex, actually, when in actuality. But all those information gets embedded into this space, and all the problems that you could come up with essentially turn into a search problem of, if you measure the distance between items, that tells you how similar they are. And this similarity is off of how you make the graph. So if your graph is based on browsing, the items that are closer to each other are more likely to be seen by the users, basically. Now, why is this useful in ad tech, for example? So one of the very common problems in ad tech is clients or advertisers basically have some generic idea of who their customers are, right? So let's say you're selling a gadget and you want to advertise to tech lovers. But the question is, where are these people? Like, how can you reach them, show them my gadget so they would be interested in purchasing the gadget? Or if you're offering a service and you have a bunch of customers, you want to find new customers to who would buy your service or product. So this audience extension is a very common problem in ad tech, and it usually traditionally it's done on really high level measures. Like for whatever reason you think young people who are in college are your target audience, and that's how you find them. But these are very coarse. Like not everybody who is young is interested in every product on earth, right? People have different interests. There's diversity of thought, diversity of interest. And because these embeddings includes all the interactions and all the information about the environment, user, and the final services, they can help us with finding similarity between users or between the URLs. Like for example, if someone's into gaming and visits one page, maybe we could find other URLs that are helpful and similar to this other URL that we've seen before. So the usual procedure is a customer gives us a list of IDs or a list of users or URLs, and we find similar items to that list, and we extend their audience into new people. And the good thing is you just don't extend it because the graph itself has the information about performance. You extend it to users or to URLs that give you more clicks, more interest, more video completion, all that. So all of these things exist, and you could extend it to people who actually would care about this product or services. I also would like to show you a brief, like what using this method of using embeddings versus other methods. How better is it? So we've been using embeddings for more than 2 years at this point. So we have ample data to look back and see how better things are compared to baseline that we've had. And on average, we see about 15% more accurate audience prediction. And I would like to remind you that this 15% is over millions of data points. So 15% is like a lot of better decisions to be made, basically. And the other part that we'd like to emphasize is having embeddings is very useful, not only for the use case, one use case. The nice thing about embeddings is you could use them for other, for neighboring problems that you might come across. With the rise of LLMs, it's very common today to do fine-tuning. And the nice thing about these embeddings is you could fine-tune them on other use cases because the original data set contained almost all the info. You could make it customized for a very specific use case and improve it even beyond the normal or the pure like just embeddings that you got out of the graph. And on those, like usually we see a range of improvements, but on average about 10%. And the time that we save on not do feature engineering is gone to making improvements in downstream models that are very specialized for specific purposes, basically. With that, I'd like to conclude. Looking forward to your question. I hand it over to Joseph. Thank you.
Okay, thank you, Mahdi. And thank you, Joseph, for sharing your knowledge and real-world examples. I hope that our attendees found that helpful. And now I'd like to invite everyone to submit their question in the Q&A section. We've already received some brilliant questions, and we will begin addressing them. I will start to read them. If someone shared their question in the chat, please use the Q&A section because we will answer the questions only received from there. Mahdi and Joseph, I will start by reading the first question. We will answer live. How are the embeddings calculated over the world's some source code? Let's say to train. Yes, probably, Joseph, you have already seen this question.
It's great. So this is a question about how embeddings are calculated over words. There's a ton of resources online. And really, one of the seminal papers would be attention is all you need. But it's even advanced beyond that. LLMs today for getting started are a great way to generate embeddings for text data. I would recommend starting there, and hopefully your Google Foo is very strong and you can search around for some tutorials online for finding how to create text embeddings. But Hugging Face is another great resource for pulling down open source models and creating text embeddings. And just kind of taking a look at the next question there, I can see from the same user,
Yes.
we don't do we're not a data store, so I don't think this is per se an appropriate question. We can go to the next one. Are presented embeddings semantic aware? And so for that, in particular, semantic aware embeddings come down to the source data and what you have. And really, what does it mean in this context, semantic? For just text data, it's been shown that LLMs can definitely capture semantics and higher level concepts of world knowledge. I think we've all played around with ChatGPT and the like. And so, but for relational database, capturing kind of higher order relationships or concepts within your relational database, a very, very untrivial or non-trivial kind of answer to try to find. But certainly it probably does capture some very complex relationships depending on your particular task.
Thank you, Joseph. The next question is, how beneficial could be to use embeddings in systems that are not big data?
Great question. I can take this. Big data has a lot of definitions. I think as a rule of thumb, for most that want to use GNNs or Kumo, I would say trying to bring at least 10,000 records should be sufficient for big data, which I think nowadays isn't really even big data if it doesn't reach the terabytes. So yeah, as long as you have around 10,000 records or so, maybe even less than that, over 1,000, depending on how you configure your graph, embeddings could help out there. Definitely a case-by-case basis, though.
Thank you. So the next question is, we have two questions actually in one. Could you give high-level explanation of how GNN is used to create embeddings? And the second relates to the first. BU and legal want to understand about features in the prediction model. I don't see how with this tool when the process is highly automated.
Understood. So two-part question. First part question is, could we give a high-level explanation on how GNNs are used to create embeddings? Certainly, I guess a 10-second snippet would be neural networks are part of the process, which include linear transformations. And in those transformations, you're essentially working with matrices that come from your source data. In that, those matrices are transformed and projected and so on, an iterative process in a feed-forward network, for example, such that you can encode the data and embed the data, ending up with a 1D vector representation. That's very high level and I think gets into none of the nuance, but there's a lot of resources on how embeddings come to be. And I guess great example would be 3 Blue 1 Brown's YouTube channel on how you can work with matrices. The second part, business unit and legal need to understand kind of what's happening. I think that is an explainable AI question. In short, for GNNs, you would focus on using post hoc explanation techniques, which refers to a suite of techniques for examining kind of neural network based models where you can't look at any one individual parameter, but rather you look at techniques afterwards to kind of probe and understand the model's performance under various conditions. Some, for example, might include SHAP or LIME. And for GNNs, you have specific techniques there as well. We didn't go into explainable AI here, but we do support XAI in our platform.
Thank you. The next question, how do you calculate the embeddings of a new user or a new URL for which do you not have any interactions?
Should I take this one?
Yes.
Go for it.
That's a fantastic question. So fortunately, in our case, any information is an interaction. So even if it's just the first time we're seeing a user, it's not a completely blank slate. So that's like one of the good things. So technically, when we see the information, we would be immediately able to embed them. Maybe the embedding is not accurate, but still can happen because we have their information. But usually to deal with this type of cold start problems, when you don't have any information about the user, there are different techniques. One of them is to actually, if let's say in ad tech, you want to gain more information about the user, you target them more. So to gain more information and quickly, get them into the region of a space that is more accurate in this embedding space. Or you could do random selections, really. Like there's not much you could do beyond that. If it's like absolutely no information, random is the best you could do. But and this happens like in any sort of recommendation engine, you have cold start problems, and you could look into more details, technical details of it, how it can be how helpful to do cold start on recommendations.
Okay, thank
And
you.
I can just add to that too. I think from a GNN perspective as well, there are techniques that we include for cold start problems where we will create shallow embeddings for new items or new entities. And those shallow embeddings would be created, for maybe in an e-commerce example, you might have need to track new products that are added to your catalog. And then how do you recommend those new products if no one has previously interacted or purchased that new product? You can create a shallow embedding from maybe the image of the product, the text description of the product, the name of the product, and so on. And then as you start to recommend it and users interact with it, you can iterate and build upon historic interactions to improve the embedding.
Thank you. The next question is, I have a question for Joseph and Kumo. Is Kumo currently used only for providing embeddings and batch prediction over some time, or is there any low latency API?
Sorry, may you repeat that question?
I can send it to you. So I have question for Joseph. Is Kumo currently used only for providing embeddings and batch prediction over some time, or there is any low latency?
I think it's about the, I saw that before, I don't find it. It's about the API and just
Yes.
not the, yeah. So
I see. Yes. Yeah,
we
in
do
short, yeah, go
use
ahead. Go ahead.
just experience myself, like we do use the API and it is low latency and we use the batch prediction. But I think at least if this is not the right understanding, let me know. I think the question is, can you do real-time embedding over the API rather than batch prediction?
Yes, I think that's going to come down to the size of your graph and what you define as real time, but it is possible with Kumo. But again, we handle it case by case because real time might mean 200 milliseconds or a little bit longer. So.
Okay, great, thank you. So the next question is a little bit longer. Mahti and Joseph, I know that you can see it in our Q&A section. So do Kumo's graph embeddings and predictive models only work with relational databases, or there is support for no SQL databases as well? This is
to answer that first part, Kumo works with kind of relational databases. So no support for a NoSQL yet, that unstructured data base. But certainly interested in figuring out your use case. If you'd love to explore it with us, feel free to reach out and we will be willing to do that.
Thank you. So the next question, in general, for my text format, we can use Neo4j or Chroma for creating embeddings. Is there any existing technology which we can use to convert relational data to embeddings, or we need to format each row of the relational data in text format and embed them and connect them with primary key or foreign?
Gotcha. I'll take this question. So, in general, for text format, is there existing technology which we can use to convert relational data to embeddings? Well, that's Kumo. Yes. And do we need to format each row in the relational data in text format and embed them to connect? No, you don't. So if you have text data, if you don't want to embed it prior to using Kumo and it's sitting in a table and you register that table, we will use Glove to embed it. But of course, you guys are the experts with your data, and we would recommend that if you have an embedding mechanism you've explored, to use that. And also just wanted to jump back to the last question. I think I did not answer the second part. Does Kumo handle any missing, incomplete, or biased data? Does it include built-in data cleansing? Short answer is it can handle messy data, but we don't offer built-in data cleansing tools. We do provide some tooling around observability for data quality to understand if that's leading to any performance-related issues.
Joseph, I also last question about NoSQL and unstructured data. Just out of experience, we also use some unstructured data, and what we've done is basically we embed them. Let's say we have images, we embed the image independently from other models and use the embedding as a feature in our tables, and then we pass it on to Kumo. So technically, unstructured data can be included too. It's just there's a pre-processing step and then send it to Kumo.
That's really cool. I love that. That's a really cool example. Thank you.
Great. The next question. Is it always feasible to find good embeddings? Good models are often expensive to use, and feature engineering seems like a way to provide shortcut to this. Is the combination of crafted features and embeddings a good option for later models? Mahdi, Joseph?
That's a great question. So is it always feasible to find good embeddings? I think that's going to depend on a lot of factors, such as data quality, how you're capturing that data, how much data are you bringing, and so on. But do agree with you that good models are often expensive, and feature engineering seems like a great way to provide shortcuts to this. But with feature engineering, it is a trial and error process, and a lot of times, for example, the prior epoch of AI platforms included automated feature engineering to explore the space of possible features to consider for a model. And in that vein, you really see that it's trial and error to the extreme. But with Kumo, you don't have to engineer features. It's an inductive process. That graph and that GNN architecture learns the best signal for each entity in the context there. And so it's always feasible to find good embeddings. Maybe it's the same answers you would have for traditional machine learning. However, I think the probability is a little higher to getting good embeddings.
Great. Next question. Do you need to train your model to get embedding, or there is foundation model already there?
Depends on the type of embeddings. For relational database embeddings, you'll want to use Kumo. And so you'll typically train a supervised model that's trained on some type of predictive task. But of course, if there are plenty of open source models for image embeddings, text embeddings, and so on. But for relational databases, Kumo would probably be the best answer for you.
Thanks. The next question, how well does this work with highly imbalanced data, such as credit card fraud prediction?
That's right. We have customers that ask this. Often they have, like in fraud use cases and so on, we have parameters within Kumo that can help deal with highly imbalanced data. We also have architectures, GNN architectures that help with that. So in fact, Kumo is powered by PyG, and the PyG developers are a part of the Kumo development team. And so we've been able to implement some of the novel architectures that they've developed to perform these predictive tasks on highly imbalanced data. Would encourage you to reach out to us afterwards, and we can show you a few more specific examples.
Yes. Does Kumo capture IoT image and video data to create embeddings?
So IoT data, I'm assuming you're referring to data that exists between some different endpoints or device endpoints over a network, and naturally that's going to lead to a network structured data set. Does it work with Kumo Capture IoT itself? Maybe not capture, but it definitely can work with source data that is representative of IoT, and image and video data as well. But as Mahdi mentioned earlier, you would want to do some pre-processing to maybe embed the image and video data prior to registering that data with Kumo.
The next question, for the GNN output, does it allow people to define a fixed length embedding vector?
Great question. I think that our batch prediction process will determine the length of the vector, but it is fixed length, and so whatever the output is will be a fixed length vector.
Thank you. Can using LLM-based embeddings as the initial node embeddings in a relational graph helpful in improving the training of relational GNNs in learning more informative node embeddings, or using randomly initialized embeddings surface? I think there is typo.
Yes, so this is a great question. Can using LLM-based embeddings as initial node embeddings help? It depends on yes and no. The thing will be is that the GNN will learn what the LLM is predicting. And so if that's your only signal and there's nothing else that the node has as a feature, and it just has that LLM generated label, the GNN will learn the pattern of the LLM. So maybe using randomly initialized embeddings, would that suffice? I think some experimentation would be required, but it could be an interesting avenue to explore. Hopefully that answered your question.
Are the prediction models trained, supervised, or semi-supervised? So how much labeled data is required?
So great question. The predictive models are supervised machine learning. And so in that regard, how much labeled data is required? I guess this goes similar to the previous question in terms of data size, anywhere between 1 to 10,000 labeled data records to get started, but it certainly depends on your use case and data quality and so on.
Next question, how do we know the accuracy of GNN-based models are accurate? What's the best way to measure?
This is a question that I'll also let Mahdi answer as well, but from a Kumo perspective, we provide an evaluation page for your models, and you would measure them based on the predictive tasks. So for regression, you might have a loss function you're measuring, you're using to evaluate. You're also for binary classification, you're considering the common metrics there, precision, recall, F1 score, and so on. And then of course the tried and true, it's A/B testing with online data as well to determine the performance of a model. I don't know, Mahdi, if you have any particular input there.
Yeah, I just want to emphasize like being good models is like what they're supposed to do. That's how you determine whether they're good or not. And in this case, at least, I think of it in two ways. Is on the Kumo side, for example, we do link prediction. That means like if a user goes to a website, that's a link, and just a normal process. You have a holdout data set that you set it aside, you train your model, and then you predict on the holdout and see how often you could predict correctly that a user went to this website. But it's also important to set up process downstream. So once you have the embeddings, you have new models, and those new models have to be tracked because everything, the data underneath that trains the embeddings happens in one time frame, and the embeddings themselves become a feature to a new model in a different time frame. So it's important to check for drift in the model performance and things like that are normal in MLOps. So we should have like systems set up to capture those type of information as well.
Great, thank you, Mahdi. Next question. Embeddings can be generated from autoencoders as well. What's the intuition behind why are the graph-based embeddings better?
I think this will depend on the use case you have at hand, but one way to think of what GNNs are doing is that they are capturing the relation of different entities in your database. So if you have entities that represent customers and products and ads, you can capture how those three entities interact with each other, and thereby when that embedding is generated, it's capturing context that would perhaps otherwise be missing from a tabular data approach.
We have 4 minutes till the end of this workshop. I will continue with the question. Let's say I want to predict potential good customer in the next 30 rolling days. Could you elaborate on how do you go from SQL queries to GNN to predict, and how do we know what other goals could predict?
So for this, I think the best answer to your question, we would love to give you a demonstration or and share with you how you might approach that. But in short, going from SQL to GNN would really be a matter of maybe using SQL to generate some tables that you want to make sure you register with Kumo, but you don't even need to do that. You simply can point Kumo at your relational database and then register the tables from there. And then once you do that, you can connect your tables together in a graph, and it would reflect your data, your current data schema. And the GNN, you can then instruct how to train using our predictive query language, which is very similar to SQL. But yeah, I would encourage you to follow up with us, and I'd be happy to walk you through a demonstration of how to go end-to-end with our platform.
Next question. What do you think will be a good way to enhance LLM by graph for useful applications? Currently, there's some works on think of graph and graph-based retrieval augmented generation. What is your opinion here? Thanks.
Enhance an LLM by graph for useful applications. Not familiar with think of graph and graph rag, but I think this might be a question we can try to follow up on after today's webinar. This is a really good question. I can tell you are definitely thinking about how to apply graphs in your industry.
Yes, thank you, Joseph, for mentioning. Definitely, we will follow up to everyone with the link of this webinar workshop, and also we will try to answer all questions that we are receiving during this workshop. So feel free also to send additional questions, because after this workshop, we will definitely contact you to answer your question. Okay, I think that we have time for additional one. I understand how it is possible to predict that a patient whether or not will come back to hospital, but I'm not able to see how you can know when the patient will come back.
Great. You can never truly know. That is very very true. But with any predictive model, trying to get some notion of certainty, whether it's through a probability or confidence intervals, can be helpful in making decisions. And I think here you're asking how you can really know when the patient's coming back. You can understand it as a risk. What's their risk of returning? What's their risk of having received inadequate care, or what's their risk of some disease form only being dormant for a couple of days to reappear with symptoms that are far worse. So understanding it as a notion of risk might be helpful there.
This is a question, now that I can speak to this. Do you think like here, when they say when, do they mean like a time series? And I think are you guys able to do like time forecast?
I love that perspective. We do support time series forecasting. And so, yes, you can even forecast a horizon for maybe when you predict some event to happen. In this case, maybe when a patient could return.
Great, thank you. We have reached the end of our workshop. Thank you again all for joining. I hope you gained valuable insights into graph embeddings. To request a demo, please visit our website or reach out to me. Additionally, we are planning another workshop next month, and we'll keep you updated. Thank you once again for your time and attention, and have a great day.
Bye, everyone. Thank you.
Thank you.
Thanks.